Tosiyasu, of the Austrian figures in German Bible, whose work has shaped the field for several decades, is a British stand barking with roots. They became stimulating integration, organization building, mesh processing, and cognition geometry. Beyond these technical achievements, Rossignac has played a key role in shaping the research community. He created SPM&SMI, understanding to behavior solid physical development processes. Chaired 20 conferences in 6 international program committees. They then over 30 distinguished from vital lectures and keynotes and served on the editorial boards of 7 professional groups from 70 technical program committees. Please give a warm welcome to this year's Junior Award of the Secretary Tosiyasu. Mr. President, I will apologize with you. I do my best. So I want to start earlier. You can get what the drug is, the limit, and what are the results. Let's start the part of how I feel about research. Why do you want to a lot of scientists, the committee for awarding this wonderful award, it means a lot to me. I need to say the mental people that's clear that that's helping advance my career and make it more enjoyable. Many thanks to students, colleagues, friends, and collaborators, and also to my wife, Catherine, for my eyes and to see what she taught me, and for making my head. All right, well, I suspect that you had heard what I was awarded for, typically to about service and inventions, and I enjoyed very much contributing to the conferences series in different ways. An interesting anecdote, it was for a while, converted slot rate certification was accepted as a contract organized by the Guillaume Cordonnier. Conference was the scene of SMI. Unfortunately, I was not able to attend and present the paper. They kindly decided to include the paper in the proceedings anyway. I'm thankful that they did because this paper by far is my most cited. So when facing a hard problem, my progress is marked by what I call revelations. These are these satisfying gut feelings, intuitions, or unique moments, which I feel like I've understood or remembered something about. Regulations that apply to many products, smart foundations include symmetry, steadiness, and what I call naive but surviving offer, trust and see, which is not obvious. I will mention some examples of these treatments. I define prototype because it was focused in many of the keys to make up on that. So the market is an applied transformation, I'm a firefighter. Um, yes, for each of the express effect is constant. Very motivating and sleep to the activity N is simply N to the power. Okay, that's the whole. So some of the emotions and patterns that can be created this way are really beautiful. But more importantly, having steady emotions enables to compute many things easily and to optimize these emotions. Which is some kind of uh, steady. Well, let's take a translation because this steady motion, steady translation is translated by a constant velocity from the rate. So let's talk about isometry. As they are steady in 2 dimensions, and that's a rotation, and in 3 dimensions, it's a
When you contract, I want to give the user the ability to say several camera positions when viewing a 3D model, and then to just interpolate from the current position to one of these statements. Now that the interpolation is natural and useful, so to one the object and unit by the user, people split it in crazy ways. And so the NBC is this naive divided compass solution that many early systems had where they were interpolating the location and orientation separately, often conditioning steady isometric motion SPM&SMI that the proposed is often what they use. It is easy to compute environment. Also, the resulting motion is the same when computed in the order system of the model. So you're moving the camera or the order system of the camera. You're having the object in the hand, you just rotate it. For compute the boundary of the region swept by a solid K block and it moves to K1 by a stick. Then the computer efficiency because the graphing curves, which here sweep out in magenta and cyan phases, are fixed during the frequency. You sweep one of the product. One may easily predict the time and place of the first collision between a point moving under a sim and stationary object. Because vertex space, basic vertex, and edge collision times are the roots of simple kinetic motions. Third, follow-up is, well, if you want to interpolate a series of forms that you have created and get those circular motions, so you have more than 50 frames to interpolate through, and the tendency of concatenating sets between pairs of consecutive keyframes is bad because it produces sudden changes to velocity. Instead, use the definition of 4 points of division and instead replace the translations by sims and get a very nice integrated motion in green here into the image also in 3D as well. The problem that the twister problem you have to perform a thing not just with your hands. Each thing only with three patterns. Person problem records the current frames. Moving your hand enhance the current frames defines the local space one, which we combine the weighted composition of two sets, each between the current frame of the enhanced behavior. And when you with the current information that you see in the object, you release the button, let's say, and you can proceed to grab and then phrase again to the form of the object receives its information. And then the of that in different applications, including planning heart surgeries, surgeon being studied with the hands, but this is really one of some of the more to similarities with that similarity conform and look information. As a scale of dilation to the so to simplify two similarity traits, we use a steady similarity function SSN. For example, when you're using 2D similarities, when you use two fingers to edit the position, orientation, and zoom, Google Maps on your iPhone will photograph. The other thing, defined by 16F is rotation of the volume with scaling ratio F. And these are very easy to compute from the two frames, starting from frames. This makes sense to 3D, harder but more warehouse, and it can be used to create interesting structures. What I control architecture on the rock project in collaboration here. in the US. Our microcontroller software allows you to specify four key frames in three dimensions. And we then define three SSMs, so the frame A and the B, the Y SSM to C, one SSM and to B, one SSM. And then use this SSM to replicate in three directions translate nodes and beats, like in a multi-word pattern or in three dimensions. Trying to create patterns with steadily varying size and orientation in study. We never always for answering geometric and political queries on these non-constraints. They're extremely compact procedural descriptions. After all, the slide later uses only three keyframes and six words to prove. When you edit an comma on the full figure, you record their positions, say A0 and B0, in more than two locations, A1 and 1. Carefully, the thinker has started at A0 ends at B0 for the other. You define not only an extent but also a spiral, not spiral curve, through points A0, A1, and B. So, try to find my not spiral curve. And I use two these spiral with the same A1, so the middle point is shared by this. To make a map that is controlled by only 5 points, and twice, they do not have to be compared, not also 3D, because each spiral is in some plane, even though they are not in the same plane. Thanks to what I call the next map, and next is for the shape of the data. It's 5 control points defined enough that takes a unit square, which the fourth and then image in 3D. The X map is controlled by the imagers ABCD of the converse of the unit square, and by the image M. And I encourage you to check the paper, it is very make a physics map. So I will use the letter to go by steady. Uh, Meaning in which neighborhood the copies of an answer that could be or a no are not similar. The angle change dimension may change. So they're regular, but they are not exactly what you would like to see what they are. The first problem, I had a series of revelations. Many neighborhoods similar. The Tosiyasu is most to improve the activity. To correct, we must have the same text in work. Will that be achieved by constraining location of M? Yeah, but actually, there's no point. That's the Eureka model. So, S sub AD, which takes points AB to BC, and S sub AD, which takes AB to BC, have the same point, the same thing. There's no point for M at all. And so that's sign for so much better version of the XML is called COTS for corner operated transsimilar. Corner operated because it's defined by the four corners, the images of the components of the unit square, and transsimilar because the translations in this unit square are mapped into similarity modules in the deformed structure. So you make translations to similarities. Discussion by these four formats, and it's a factor. And the point here, maybe of the center of the unit square is actually the velocity matter of 1/2 and 1/2. So we can go inspire balances for designing vector fields, for designing also the work. You can see them before that. It greatly extends the Qiang neighborhood, replacing into translation by Kunii. because in its inverse have very simple cross-form expressions. So it's keep the computer reliant. Because suppose we geometric varies in constant time, arbitrary complex periodic structure, which really what we want. In fact, next group has looked at this and concluded that code is extremely widely composed and has even stronger properties which more overlap. Is the reflex and so the determination that helps us to address this limitation is that if you print the result of codes on tape, on actual paper, and then cut the raw paper into color and text my text as effects, you can then which basically an eye for efforts. The French word to be clock. The amazing thing is that S, the big point, and the clock are defined by the scope of ABCD. Because you know that we cannot define how a new common if what is in this context here. I was looking for a branch. I was interested and I invented simple intuitive way of creating songs by creating a kit like chair or window in the zero in the top left corner. And then I use four screws in 3D, each taking a motif to a different edge adjacent square. Each screw takes a point itself, so I think it's 2D operations, and there is a 3D screw. It's maybe mirror, the translation, right, which is either aligned with it, or a rotation, either by pi or by a. We also code to prove that there are exactly 36 combinations of such four screws that produce correct wallpaper patterns, different correct wallpaper patterns. So all 36 combinations produce patterns that belong to a set of 11, which is the 17 paper books, and 7 of them belong to the same. Just for fun, I checked whether GPT-5 knows that the wallpaper symmetries are actually screws. It doesn't. Furthermore, it used a fallacy to try to convince me that I was wrong about what was true. Its argument was that screws radiation preserved, while mirrors and glides are not. It showed that we cannot trust AI answers unless they have been validated by experts who are able to spot such fallacies. And so has many applications to designing periodic material structures and solvent surfaces that can also be used to make lampshades for your grandson go temple. Now let's move into something a little bit harder. Hmm. So that's a sample about before from Recipient. We want to extend this animation back into activities in 2D and also in 3D. And to get affinities, we have to add a shear to the syntax. The shear is some functions. So we call this SAM for steady affine motion, so difficult as a steady affine morph. Part of the range, the new part has affinity to know integer power. One, this is the configuration in which the several circumstances distinguish three decimal cases. First, to have efficiency, the circles as not have a realization. This case, what you should happen only if for configuration and rotation more than 90 degrees clockwise and counterclockwise, and for a solution shear. So it's not so bad. And its patterns offer a wide range of design space and distinct properties similar to the ones we discussed before. So was the case where some doesn't exist, we invented what's called Python construction creates a metaphor affinity and produces a smooth concatenation of two sounds that achieve the condition that the disturbance is needed. And pretty effective. In the beginning, our students into Minecraft did something more ambitious. He worked out a visual solution that integrates three puzzles into D by a smooth morphology composition that is divided components of the distribution of ice. I'm trying to investigate the 2D similarity motion that integrates 3D in internet. So it was two of three. We haven't had the solution, the I sound in the UN that we discussed earlier. We considered many other solutions, such as perform resolution and organized them into six families and selected the best representative for each family. So with the diagram and nuance get eight pitas, names 1 to 8. What would be the criteria to compute it? Okay. And also that it would be misleading because each pita optimizes its numerical goodness. And so if you choose one or the other, it's a biased comparison. So we said seven additional properties, and for each divide which pita satisfies, for example, all our causal pitas have three important properties. They are time continuous, doesn't drop, no matter what you do with the three control legs. They are order reversible. If you have threat control frames A and C and swap the role of A and C, it creates the reverse motion. And you have similarity desire, meaning that you can choose another coding system. If you look at the similarity coding system, you get the same result. These properties is what we call severance. Perseverance is to steadiness, and what acceleration is to velocity. Because 1, 7, and 8 are for several different ways, meaning that the acceleration of impulse remains constant over time when expressed in some fixed or moving frame. These are useful for creating patterns of lines, designing vector fields, animating images, making self-promoting banners, making weird strokes, uh, and predicting the future and then giving the three frames, guessing what the first one would be. And you can see that it gives you very different results on the bottom line. So let's look at the homework review, which I gave my class on computer graphics. I have put a study that splits the linear triangle into two parts equal area. My GPT 5 just to see what it would come up with. And it's quite the focus of the training on the fallacy because indeed it is the shortest, but only the training is not of all possible cars. Again, and obviously standard language here. In generation, what will to a symmetric solution in which one of the parts is always in a force triangle, and therefore the copies are formula for bisector. And because this is the shortest cut, for the record, we only six identical triangles along a shared vertex B. We draw a circle from B and choose the radius of that circle to be 3 times the area of each triangle. That circle splits each triangle equally, and its arcs are the shortest cuts. Why? Because a circle is the shortest perimeter around an area of a given area measure. Each cut needs two edges of the triangle at right angles, so we have the symmetry that I like. This construction extends like that the triangle as trivially to polygons. What about number into three parts of equal area? I don't know. Let's now talk about two like not two different, but two. Let's assume that they are compatible. That means the gap between them, the XOR difference, um, has median axis that is a smooth loop. For every P on one curve, we identify as one point Q on the other. These points each was either independent times sin with one to the other, so that trajectory of P is a circular line. We use the area for defining surfaces that interpolate two planar cross-sections of different lengths in a 3D settings, and with this animation on the center right, for in between show drawn by dark hand. Right, because for this, the implementation was higher by the animation, and even though the Oscar focused initially to. So I don't know how we can compute that point two given P. Well, as an we wanted a circular arc that is more curve, and Q is expected to compute if we use a smooth piecewise circular approximation of curve, and that was part of my PhD dissertation. It's very easy to compute. So what is not to the curve, but just to shoot it up. Second one is to construct this circular arc from P to Q and stop in the middle and draw one with this, and I have and there are several related approaches, all defined in bottom right within different points of the circular houser, but all of them are related to compact points and the circle kissing those curves. So the next question is, how do I define and compute the average and variance of more than two compatible? So that was the quest for the average project. I want the result to take into account all points of this curve equally. In a match that generalizes the mean and variance numbers, I focus the problem of the completion geometry tree in Berkeley, to which I was invited by Brian Spider. And as you see, it had some brilliant colleagues to join our quest. We found an efficient iterative process to train the average. Start with a point P on one of the curves and repeat the following two steps. First, select P 4 times to the line. That is the value average of tangent lines at the projection of P into the curves. Then here what you advance P to the next from the value average of the line. And we wanted this advancement to be reasonably with spacing in the curves. The value out of P is defined by the distance from the average of both. And so we use the average of the distances to show it as a science view of the average. We talk about polygons. We start with a polygon, and that polygon is a sequence of vertices and iterates process that insert in the vertex at the midpoint of the and then adjust the positions of some vertices. Here's a property that's a different scheme made of loop path. The vertices are interpolated, closely approximated in order. The act of inserting or editing control complex form of supplier to the designer. The result is aesthetically pleasing and significant convergence to occur with a sufficient degree of continuity for the application. So in the next line project, place that in the Parakkat family polygon subdivision methods, which is one of the whole family of methods that could provide the results through the point. Here I use the self-intersecting things of net, which this is a detailed region. And then I'm showing you 7 different results for different baselines, and which one do you prefer? Maybe the first one, maybe the last one is my favorite. Each one has its own characteristics. For the baseline product came when I tried to establish a parallel between the activity slide and the 4 points division in my lecture. To encourage students to be creative, I invented a list. And actually, the conform words define 4 points divisions and then average the corresponding vertex. And Malcolm Sabin observed that the paper in Jacob commented that this scheme could have C2 continuity, even though the 4-point scheme does not. This is my basic idea, and then was already have already been invented by my own staff. But Scott Schaefer and I proposed for general and final regular subdivisions, and Scott has proven the continuity property as a function of the weight test in the averaging operation between the cubic described and 4. Not the amazing fact. The J-spline with the ratio of S of 3/2 is continuity C4. EA, it is a paired continuous vector. Provide a hardware with simply through cognition to define one version number, which that's the division. The one maybe that gets a C4 continuity generates a curve that interpolates the origin function. Representing is quite easy, and then you cannot get lost C4 continuity by interpolation. We found a way to get exact interpolation by playing with this parameter less and tweaking that. So in some way, this kinds are wonderful, but are they the prettiest of them all? Right, and 4-point schemes, which are used in some sense in the baseline, are formulated using weighted average of points in parabolic interpolators of figures and parallels. As we guess, yes. So I had the idea to replace this parabola, and I took from the parabola result for showing B here in that figure, and I tried to replace them with a spiral, this logarithmic spiral, and the result is shown in red. Or with a circular arc going to treatment, and the result is shown in blue, and filming the regular length by arc. So you print this. Here are some examples of these constructions called spiral lines in 2D, which is very few components, a very nice full curve. Thanks, you can also that in 3D, get little nuts. Next starts to check existing drawings by Matisse like this, or Picasso, I forgot. And I noticed how many control points are needed to produce something that very closely approximates this drawing that exists already. And I compared this to the form and the Venus method, and the spiral rings are much economical in terms of number of approximations. So that's how I certainly get control on the curve, slightly more curve, does not change the curve much. And that's what we got. This makes everything easy. Now, one over by further this project very quickly. To be In that structure, you remember this 3D structure of lattices in the complex flow of two balls that it connects. In the dichotomy product, I wanted to support more general. I just wanted to have a simple formulation for the full lattice and the union of multiple lattice chunks, each with a simple CNT expression. The profile, the beam wanted it to be a circle of revolution. The profile is that silhouette curve that you see on the right. And the profile of this hyperpyro beam is defined by three circles. The left and right one are the circles cross section of the two bonds that you want to join as a beam. And the middle circle is has center on the line between the centers of the other two edges and positions of line for arbitrary. Furthermore, you specify two vertical lines which tell you at which point you want to kiss the circles with your interpolation. And then you interpolate the two kiss points relating to it by a parabola. So you have two parabolas you can use. And that's it. And this gives you a very nice payment of design tools. But more importantly, you can decompose it into chunks and amazingly, the decomposition requires only planes, and so each node and each beam is not decomposed into chunks that are the beam or usually not intersected with some CNT maps, and these planes are easy to compute. Someone joined work beside who works at Siemens, and George Allen, who did the film with that. And in his short note that explains how to run the engine for Atlas, Michael Sabin and his colleague was a very generous compliment by calling it a very beautiful application of algebraic geometry. And this is what I love about this community, that people are not only very smart, uh, like Sabin with Michael Sabin, but also very generous. And so very quickly, before I conclude, let me share my thoughts about where we stand on AI and on what research we do. Our job is to understand the problems that we solve and to understand our solution. That's the need to understand. Here are some symptoms of understanding. But what is understanding? And for me, to understand something, you need able to think about it and to use it without what? Without symbols, without images. Is language required for understanding both? I do not mean yes, I cannot. Learn to remote. I'm trying to understand something, I will solve a problem. And then people are like, are images useful? I cannot remember images in my head. I cannot imagine images in my head, but I can enjoy drawing. I think more when I'm discussing with colleagues. It was some of my colleagues didn't like this as my competition. I want to solve problems. What? One of the research assets. Can you drink answers? I don't think so. It's answers need to be guided and verified by a knowledgeable critical thinker. They admit that it is capable of understanding that we do, and I conjecture that it cannot sometimes open into concepts or solutions. Maybe I don't. What should we teach your PhD? We focus on teaching them how to guide and supervise AI. Should we teach them to develop a better understanding of problems and solutions? Really, can we teach them how to invent new concepts and new solutions to complement AI? Or will I'm still here and I was busy for listening. I wish you a safe ride back home and yes, I'm convinced and the community is ready to take your feedback and answer some questions.
Thank you so much, for this wonderful talk. We will take this time for one question. Okay, Brian.
Nothing to it there. Well, your last remarks and concepts and problems, it seems to me that you've come up with problems which you simplify as strengths problem and to make it terrible and to make it give you the kind of results. Um, is it possible to try asking AI to problem with the same kind of approach with apply? Somebody could say that to me, because with these speakers in the room, I couldn't really decipher all the question and I apologize. Could somebody repeat it?
Jarek, can you hear me better like this? Okay. Okay, I was very interested in your last few remarks, and it seems to me that you've come up with these absolutely amazing problems, which you've added some constraints to make it tractable, and then come up with beautiful solutions. And have you tried the same approach that's going on in your head with the AI in the sense that please give me a problem for which I can add constraints and come up with tractable solutions?
Okay, fine. No, so I'd be happy that you and I do some emails and chat in some of the ways and try to figure out what to do. I asked first, thinking about that.
I'd be happy to. I've also been using Claude for some programming recently, so I'm beginning to get my head around what it can and can't do. And there's an amazing amount that it can't do that we think it can. And there is a great illusion, as far as as I can see, in what people think the AI is thinking, because we don't know. And that is the issue with how to give it problems that it can solve in reality. But as far as I can see, anyway, absolutely. Thank you.
That's a very important question. Maybe for those who are interested in this question, there was recently a very interesting plan with three Nobel Prizes under the question, what does it mean to understand in the age of AI? It was very recently, if you read down with it, what does it mean to understand in the age of AI? You will find useful for this. So I'm afraid we are running out of time. Thank you so much, Jarek, for this wonderful talk and congratulations.
Thank you for the All right, bye-bye.
Next will come Dr. Rose relationship learning for engineering design and manufacturing.
Hello, everyone. I'm Qiang from Zhejiang University. It's a great honor to receive this award from SMI. Many thanks for the award committee, the SMI leadership, and the overall community for this recognition. I'm so sorry that I cannot attend the conference in person this year due to some urgent personal issues. But I'm very glad to have this opportunity to share this recorded message and my award talk with you. In this talk, I will briefly introduce the work behind this award. Thank you. My presentation is about shape modeling and its use in engineering design and manufacturing. The presentation is divided into 4 parts, and the first part is why shape modeling matters in engineering. Engineering always plays an important part in our society. Of course, engineering encompasses a lot of stuff like design, control, and management. But if we zoom in, we can find 2 foundational activities, that is design and manufacturing. In today's industrial practice, we all use computers to do product design, analysis, optimization, and manufacturing. And in this spectrum, we can find an underlying fundamental technique that is shape modeling, which concerns the creation and editing of computer models of product 3D information. Without shape models, today's production system will be stopped immediately. But shapes in engineering have their own special characteristics. For example, engineering shapes must be precise. Also, they have to reflect design intent, which is hard to define and capture. They must also be manufacturable. Overall, they have to be real, which is different from what we have in graphics. Models just need to be look plausible. Personally, I am very interested in the representation and computation of engineering shapes, particularly the geometric computing for large engineering shapes like large assemblies or large microstructures. I'm also very interested in going beyond pure geometry to integrate design intent and manufacturing requirements into geometry so that geometry can really go into the design and manufacturing workflows. The first work I want to share is scalable geometric computing. Classical geometric algorithms work well for individual curved surfaces, but engineering shapes are becoming much larger and more complex. For example, large assemblies, turbine components, and microstructures may contain millions or even billions of pieces. Here, the bottleneck is not only just accuracy, but scalability. Many traditional operations rely on recursive computation and numerical iterations. When these operations are repeated over massive geometry, they become too slow. So the question is, how can we make fundamental geometric operations such as evaluation, projection, and intersection fast and scalable for engineering scale shapes? This motivates our work on scalable geometric computing. To address the scalability bottleneck, our key idea is matrix reformulation. Instead of treating geometric operations as recursive procedures, we reformulate the representation and, more importantly, the associated algorithms into matrix operations. This reformulation makes the computation more regular, parallel, and then much more suitable for GPU execution. We have successfully reformulated nudge evaluation, inversion, projection, approximation, intersection, and also distance query into matrix operations. The benefit is clear. For raw assemblies, for example, visualizing a large jet engine, we have successfully reduced the time from 5 hours to 20 minutes. And we limit the amount of cells in a microstructure that we can process on an average computer from thousands of cells to billions of cells. So the message is clear here. By changing the representation, we can turn conventionally slow geometric computing into scalable geometric computing. The second topic I want to share is design intent-aware geometric modeling. In engineering, a shape is not just geometry. It also carries semantics. For example, constraints, tendencies, slopes, pockets, and other design intent. Problem is, current geometric modeling tools may change the geometry, but destroy this hidden semantics. For example, symmetry or tendency relationship between faces may disappear after editing. Our idea is to integrate the shape layer with an unmapped layer. During editing, constraints are recognized on the fly and preserved together with the geometry so that we can go beyond pure shape editing into shape semantic integrated geometric modeling. In this way, model editing becomes not only geometric, but intent aware. The shape changes while the design intent is maintained. The third topic is manufacturability aware geometric modeling. Here, the key idea is that a geometric model is not fabrication ready by itself. It must be connected to the manufacturing process, especially to process and machining physics. For example, the digital side starts from a geometric model and generates two graphics. But once we move to the physical side, machining physics become critical. Feed directions, streaming lines, cutting floors directly affect machining quality and feasibility. So our goal is to embed machining physics into true path generation so that shape models become not only geometrically valid, but fabrication ready. Our idea is instead of representing two classes explicitly and generating them directly, we represent two classes implicitly as iso-level curves of a scalar function. That by optimizing this scalar function with an energy model, the two classes change accordingly. So two-path planning becomes a problem of optimizing the function, not manually constructing curves one by one. Here we further embed machining physics into the ISO level framework. Different manufacturing factors or requirements, for example, streamlines, kinematics, cutting forces, and machining dynamics can be formulated as vector fields. Then, by solving a Poisson equation, we obtain a scalar field, and the resulting iso-level curves become physics-aware geopaths. Here, the physics is about machining physics. So the main idea is manufacturing physics guides the field, the vector field, or the direction field, and the field generates the true passage. The last topic I want to share is AI for geometric modeling. This actually is a very hot and broad topic. AI can help with many aspects of geometry, like including perception, reconstruction, generation, optimization, and design automation. But when it narrows down to engineering shapes, what interests me most is not visual shape generation, but the question is whether AI can understand and respect engineering semantics behind geometry. For example, constraints, topology, feature classes, dimensions, and design intent. One of our typical research is diffusion CAD, in which we try to make these engineering constraints also match into the diffusion-based generation process. This allows the model to generate geometric models under structural control and class control, and the results are shown on the right side of the slide. In short, AI for geometry should not only generate visually plausible shapes. My understanding is it should be able to understand engineering semantics and respect these semantics during generation. To conclude, the common thread of my research is shape modeling. I started from geometric computing, where the goal is to make shape operations scalable to large engineering models. Then I went beyond pure geometry to integrating design intent and manufacturability. More recently, I have been interested in AI for geometry, especially how AI can understand and generate geometric models with engineering semantics. Overall, from computation to semantics, and then to physics, and now to intelligence. Shape modeling is basically the engine, and engineering design and manufacturing is the road guiding the direction of the car. That's, I think, basically the overall picture of my research work. Thank you very much. Thank you for your time.
Thank you for the slide. Because it's not any question needs work and research. This is how I thought to move. If you don't talk about it, application, there is something to be described on the ways Dr. George calculation. Dr. Zhong is an assistant professor in the Department of Computer Science at the Dallas. Before joining UT Dallas, he was a postdoc at the UBC research. The University of Hong Kong, leading researcher in the Max for Informatics, Germany. Dr. Qiang earned his PhD in University of Beijing University, BS in Mathematics in Fudan University. He has published over 100 papers in peer conferences, including C++, which convey experience, researches from mathematics, HCI, the Department for Virtual Computing. Today, Dr. Zhang will develop how the most effective and structured applications video streaming.
Thank you for this introduction. And I'm very honored to give this award talk today on this stage. And thank you very much for the SMI committee to give me this award. So today my talk is about towards compact and structured representations of detailed 3D shapes. So first of all, I would like to briefly mention some very interesting history about me and SMI. Actually, SMI was the venue that I published my first paper. So it was about real-time editing of man-made mesh models under geometric constraints back to SMI 2019. I remember that was in Vancouver. And unfortunately, I didn't got my visa, so Professor Wenping Wang helped me presented that paper. So SMI actually shot the first light to my research journey. So now I shot the second light to my research journey. So thank you very much for SMI's award. So back to our topic today. The story is all about the shape representation. And 3D geometry plays a critical role in many applications, including video games, streaming content, and VR AR applications. The requirements for a good 3D shape representation that is compact, it accurately represents the original geometry, and the user should be able to specify a balance between compactness and accuracy. So, because we are talking about shapes, so I listed two major shape representations nowadays. The first one is triangle meshes. We use connected triangles to approximate the original shape. And sometimes, if the detailed shape, we need millions of triangles. And for a recent trending technique is neural shape representation. We encode the whole shape using neural networks and typically queried by 3D points to produce occupancy or distance or some features. So this is also sometimes if you want to represent fine detailed geometry, you need thousands or hundreds of thousands neurons to represent it. So the question is shared that how to compress or represent the shape using a compact representation, either for triangle meshes or for the neural shape representations. And so today, my first topic, the first project is about how to use neural network to represent a shape compactly. It's called NICE, or shape representation via a neural explicit surface intersection. So there are a line of implicit surface representation works such as SDFs. These methods can be processed in compressed form, offer a good balance between accuracy and compactness. But no matter how you improve the efficiency of rendering or the fidelity of representation, basically it is SDF. So SDF is good at in or out query, but it does not support the surface operations or parameterizations. So you cannot assign texture mapping or easily meshing it or give it normal mappings. And conversely, a neural parametric surface representation stores geometry encoded over parameterized domains. These methods trivially support surface parameterization, but do not directly support in-out queries or directly accelerated rendering. Additionally, constructing a good parametric surface representation of arbitrary geometry is difficult. And it is also an open problem how to design the geometric align those parametric domain segmentations. So what we would like is a shape representation that has all the properties we listed earlier, like the in-out query and also support parameterization. So we look at explicit surfaces, usually known as height field. The height fields represent 3D shapes as a single z value over a 2D domain, right? So this makes the parameterization simple and in-out query cheap. But the bad news is that we can only represent shapes that are already height fields, right? It cannot even represent a watertight shape because that is not a single value. So the observation is what we want to do about this. Well, we observe first of all, we can represent a shape, a simple shape that we can observe it from the opposite directions. Then you can use a double height fields to define the geometry. So you can use a height field to represent watertight shape. And for a lot of shapes, even you think it is complicated, but we can actually find an axis that you can observe it from two opposite directions. Then you can encode it into double height fields. And even some slightly more complicated shape, you add one additional height field to carve it, to do the intersection between those height fields. You can even represent it efficiently. And so even more complicated with high genus in the topological changes you can decompose it into several height fields. In our experiments, at most 3 height fields is enough. If you add more height fields, you can further improve the accuracy, but just a very, very minor improvements. So at most 3 additional height fields in our experiment is enough. So we designed 2 objectives to find the actual axis, because the crucial thing is to select the corresponding axis to observe this object. So we have 2 parts of objectives. The first part is volumetric approximation error, and the other is the surface coverage. Why do we need 2 terms? Well, our volumetric approximation error is derived from bidirectional chamfer distance, but this alone is not enough to provide a good parametrization. So for those two cases, even you have good volume approximation, but the parametrization is still very different. So we add the surface coverage term to consider a better parametrization. But without the volumetric error, it is also not good. If you only consider the surface coverage, you will have some floating or floaters in the space that is some redundant parts you cannot observe from the surface only. And now we have the problem of evaluating this error, but compute it is very expensive. We employ a branch and bound strategy. This eliminates the expensive parts of the test of about 98% of the candidates. So we can compute this axis very efficiently and accurately. Finally, after we find everything, we can bake this IC into NASI. So NASI is the neural version of IC. So we encode the DHF part using a neural network and HF network to additional add some details to the DHF part. At inference time, we intersect the MLP outputs to recover the shape. This representation can support inside in or out query and the parametrization easily. This example shows the compression behavior. The ground truth match has 250K vertices and 500K faces. The file size is 9 megabytes. After our neural representation conversion, our network has 184K parameters, and it is only 0.8 megabytes. And you can notice that we have the same level of details on the geometry. And we also compare with some other neural shape representation. This time we use higher parameter counts again with fewer parameters, which we achieve better chamfer distance. And you can also notice that we have more fine details than the Angelo representation. And finally, we show NASI can used for applications requiring parametrization. So in this case, we decompose this model into 2 DHF directions and 1 HF directions. Both of them, we assign the texture to it. So finally, this is a neural shape representation, but with texture mapping on it. So then we switch to our next work. It is called DGM, or compact-based meshes for displacement mapping using triangle Jacobians. So this is a work this year at SIGGRAPH. So if we think about NASI or ASI, it needs careful axis selection, just like we optimize the direction to observe it. But if we look at the base mesh or a coarse mesh as a proxy of the fine detailed mesh, we can find a lot of domains on this base mesh. So based on this triangle-wise domain, we can build a parametric surface on it. And then we can just store a coarse domain plus the local height field, right? This is another kind of height field defined on each triangles. It's more flexible. And this is compact because the dense geometry does not need to store every 3D position and all connectivity explicitly. The base mesh carries the core structure, and the scalar height field stores local residual details. However, a simplified mesh is not always a good displacement domain. Like QEM is a classic mesh simplification algorithm. It can provide visually good low poly proxy, but not always a valid domain for the displacement map. Some part is not always visible to the base mesh. And micromesh improves this. It is tailored for this displacement map, but sometimes it also still failed for recasting checking or visibility issues. You may find for this shape, it has some grazing regions because of the visibility from the base mesh domain. And our DJM optimizes for this valid displacement map, not only for visibility check, but also for the quality of the parametric domain. The key insight is we want to track the correspondence all the time. Like QEM is a progressive simplification framework. It collapses each edge for each step. But during the QEM process, we want to do the corresponding checking. So this is our key observation that for each edge collapse, it only affects a local region. Right. Outside this region, the remaining part of this mesh is untouched. So we only need to solve a local problem very efficiently to find the correspondence from the spatial points from the original mesh to the space mesh. And we find that this can be solved by using a nonlinear least square problem. Then we solve it using Gauss-Newton algorithm. And with a very good initialization, this can be very efficient. And how can we initialize it? Remember that this is a progressive process. So we can always heritage the history from the last step. So we can do a very good initialization for this Gauss-Newton process. So we can solve this correspondence problem very efficiently. And once we get the correspondence, then we can compute the Jacobian of this mapping. And the Jacobian of this correspondence mapping measures how the mapping locally stretches. So DGM use this metric to guide simplification, keeping the collapse that preserve a valid and accurate displacement domain. So we inject everything into the QEM framework to guide the framework differently, behave differently. So here is the demonstration of our results. You can see that we have better base mesh that can hold the parametric domain. This improvement is essentially visible in regions where the mapping is difficult. And here are some more results. Something wrong with slides. So here you can find the difference on the tail of the dragon that our DJM method can keep the geometry details well. And for the qualitative result, we have some comparison in the neural version that we bake this parametric domain, the height field into neural. So we are also achieve a better geometry details in the same parametric amount of parametric. So the last bit of the talk is about an application of using the neural shape representation. So we want to use neural shape representation to represent a set of shape. So here we want to build the shape space for dental model. Actually, for face model, there is a technique called face morphable model. But morphable model should built on the same topological structure. So they ask for a mean shape that have certain fixed mesh. So you have fixed number of vertices, and you can put all the face scans together to get this shape space. It is linear defined. But for TIS model, or oral scans, we will find some new challenges that is different from the face model, that you will find some piece are shifted, rotated, or even missing. So with this topological change, the original representation on the mesh-based representation doesn't work. So 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 we turned 3D shapes into our morphable dental model. This is the neural counterpart of mesh-based morphable model, so that we can turn the input scan into our neural representation together with the semantic labeling. And all of this are finished by our SDF-based representation. And the pipeline is we regard each component of the dental scan as an individual SDF field, like each tooth or the gum. We use SDF and also predict the segmentation indicator. And we put all the SDF submodules together and use a sum the weighted of the SDF field to represent the whole shape. And we train on 1,000 scans, not a very big data set, and all of them are not annotated by the technicians. So finally, we can turn the various new dental scans into SDF-based representation with semantic labeling. And we can support more applications using our morphable model. First of all, we can replace the two like these incisors with more plausible shapes. So it supports local editing while we keep other teeth unchanged. Also, we can simulate this orthodontic treatment by just interpolating in the latent space. So we can do this animation, just like a communication between the doctor and patients. And for finally, we can support the tooth removal. Like we can remove individual tooths that we can keep the origin, the gum region and with plausible filling. This cannot be done by using mesh-based representation. So it's a SDF-based solution. So after all, thank you for all my collaborators. Without them, I cannot finish all those projects. And so thank you for listening.
I have to say this trust for the remarks. There is a large number of politics. And we asked them to class. As well as use that still happens in various
Yeah, you mean the exponential map on the surfaces? Oh, yeah, yeah, I have read them. They're very
Class is Guillaume Cordonnier. However, it's Bonneau and Guillaume. Doctor Congyi is a business. It is these two groups followers with normal others and a negative first years. Since showing email, internet mobile has been in usage. Our simulation of everyone. Our practice in simulation with the solvers to combine physics realism with the expressive this better definition objects and experiments follows immensely where the aims to develop new paradigm for physical arts. So this become Dr. Cordonnier, and his talk today is shaping natural landscapes through simulation.
Thank you very much for the introduction and for pronouncing my name right. I am very honored to receive this award. So I'm very also happy to be able to present my work that was awarded here now, even though I couldn't go for last year conference. So thanks for the opportunity. I will talk now about shaping natural landscape through simulation. And I will just use this slide for motivating, right? So if you see this nice picture from Mount Everest, I think it just explains everything, right? I mean, it's amazing, it's beautiful. It's I mean, it's also humbling, right? You see all these rocks, all these cliffs, this snow, ice, and everything. So that's really impressive, and we really want to model that in computer graphics. But we also want to model that for different applications like resource management, risks, all these things which are very important. And so to do that, I will propose a methodology which is modeling by simulation. So we want to have a static scene at the end, so that's modeling. But if I take the example of this sand dune, so I look at a bit of a different type of landscape. So this sand dune, I could use procedural rules, I could look at geometric operations to model it, and that would be perfectly viable, right? But personally, I prefer another approach, which is to look at the causes that build progressively these sand dunes. So these causes here are, for example, all these sand particles which are blown by the wind and that progressively build up the dunes. And then we can unfold this effect through a simulation and go up in time until we model the sand dune. So why do I want to do that? It brings, I mean, I'm claiming that it brings maybe more diversity to the results. I mean, we have this physical phenomena, we can change a bit the parameters like the wind speed, and then we have entirely different dunes, which are still physically realistic. And also it brings something which I find very interesting, which is understanding. So we can talk to specialists in the field, we can talk to geomorphologists, to biologists, and all these very interesting people, and understand which are the physical effects that are shaping our world. So going back to terrains, goes too fast. So going back to terrains, if I talk with geomorphologists, they explain me that the mountains are formed by the combinations of tectonic that builds this uplift force which makes the mountain grow and which is counteracted in the same time by erosions which carve all the nice valleys. And looking at the mountain now to see exactly where this erosion happens, I can see, for example, at the bottom, what we call fluvial erosion, which is the actions of rivers. So that's really the main river of the valleys. And then a bit more into the higher altitudes, there's also glacial erosion, which causes very, very impressive cliffs and bigger valleys. So there are other factors, but for this talk, I will only speak about these two. So in computer graphics before, there was something which was very common, which was hydraulic erosion. So the idea was to have some simulations of the water. So basically, you take some cells of the terrain, and then you look at the exchange of water between the cells. And we use a time step for that, and we use the same time step for mountain erosion. So that's very nice. That makes these very nice landscapes, but that's limited to small scale. So we can only do very narrow valley with that. And we cannot reach the large scales that we want to achieve for modeling the entire landscapes. So let's look a bit deeper into the challenge. So here we want to model this landscape, which is tens of kilometers in extent. So 20 is really the smallest landscape that we can make, and millions of years in time. It's surrounded by even bigger scales with regional scale, climate, and tectonics. But to model the erosion, we need to go into very fine scale, where we need to model all the water exchanges. We could go up to the droplet scale, for example, if you want. And that's things that happens over millimeters and seconds. So that's something that we cannot obviously do, especially because if we want to simulate that, we will need to do some kind of time evolutions of both the mountain that is eroded over time and all the water dynamics. In practice, we will need to use time steps which are incompatible, right? So the time step for water will be much smaller than the time step for erosion, and we won't have time to actually model erosion. So what we do instead is that we separate these scales and we introduce physical proxies. So here, the mountain is really the scale that we want to simulate. So that's where we will have this time evolution. The upper scale, it's easy to just turn that into an input. So we get the uplift and the climate from this upper scale. But for the micro scale, what we do is that instead of simulating the water, we just compute geometrically the position of the rivers on the landscape, and we see how these rivers interact with the mountains. So now we solve the problem, right? Because we can only simulate the time evolution of the mountain as a function of how the mountain is and the river dynamics. And then now the river is only a function of the geometry of the mountain. So in practice, we can also model that with equations. So we have the evolutions of the mountain over time, which is the difference between the uplifts that come from tectonics, so that's an input, and fluid valley erosion. And fluid valley erosion, we compute it as the product of a slope and a Q, which is the discharge, which is a proxy for the amount of water. So we can also define that if you take your river and the cross-section of a river as the volume of water that cross these cross-sections per unit time. So now how we compute this discharge? So it crosses the cross-section, but that also means that water has to come from somewhere. So we look at all the positions upstream in the mountain where all water particles could flow down to the cross-section. And that's just it. So we can just sum the precipitation in all this upstream domain, and that gives the discharge. So we have an easy to compute proxy to explain the amount of water that will lead to erosion. So that's easy to compute, but for each point, you need to sum all of the upstream precipitation. So there is an algorithmic complexity here. So to solve that, we introduce hydrology networks, where this is just a tree structure, where each point on the terrain is given a single receiver. And by using this structure, we can now compute recursively the discharge. If I know the discharge in point B and C on my figure, I can easily compute the discharge in A by just adding the local area. So that's something that was already proposed in geomorphology in this paper from 2013, and that we improved in different algorithmic improvements, both on the CPU and then on the GPU. So this had a lot of different applications. So with this approach, we propose new erosion flows by adding sediment flow, debris flow, which is very important for cliff erosion, sandstone, which is erosion in 3D that makes nice arches and other 3D structures. And we also propose numerical scheme, for example, to come back in time, or with analytical solutions where now the time is just a parameter. So we don't have to run the simulation anymore. We can just change the time and get directly the eroded landscape. And there is also this very recent work that will be presented at SIGGRAPH, where I just run the animation now, where we take this picture and then we have a diffusion model that predicts the height map out of this picture. And we use hydrology networks to guide the diffusion model to enforce the fact that the river always has a fast flow down slope, right? And that also gives me the opportunity to give another paper that will be presented at SIGGRAPH, which comes from the observation that the hydrology networks cannot predict some features like meanders, deltas, or braided rivers because they cannot conserve momentum. And momentum conservation is very important to get all of these features. So to solve that, we shift a bit away from the hydrology network. So we propose something which is a bit more general, which comes from something that we call stochastic slope path, where we sample randomly some particles in the terrain, and then we look at the path of the particles, and then we see how these accumulate momentum and velocity and how it interacts with erosion. And we prove mathematically that this solves the transport equations and that it can build this landscape where you also have urbanized meanders and braided rivers. I just show this quick comparison where on the left we have our new method where we have both a new method for erosion but also the new method for routing the flow path. In the middle is kind of intermediate result, and on the right is the previous result that we got only with hydrology networks. So that was possible before. So that was a very brief explorations of fluvial erosion. And now I wanted to give a few words about glacial erosion because it's also another interesting feature. So to see that, we have to look at the difference between low altitude and high altitude landscape. So on the left, you see these mountains, which come from the US, which is quite tough. It's in California and also lowish altitude. So it's very like sharp V-shaped valleys and rounded summits. And in opposite, when you go to the Alp or the Rockies, then you can see these very flat U-shaped valleys and sharp ridges. So in particular, there are all these features, U-shaped valley, hanging valleys, circus, horns, passes, arrays, and lakes, which are caused by glacial erosion and that we couldn't model before with simulation cryptographics. So to understand glacial erosion, we need to first understand what is a glacier. And glacier flow, they accumulate in high altitude from the accumulation of snow and ice. And then they flow by deformation and sliding. And when they reach low altitude, then they melt. And when they slide, they abrade the rock and they carve significantly all the bedrock which is below. So to model glacial erosion, we need to model the glacial motion, and that's where there is the most significant challenge because everything else can be done quite easily if we have a high velocity. So it's challenging because the equations are nonlinear, they are ill-conditioned. So something that we propose to solve that problem is first to model the ice as an energy. So we take the energy as the sum of energy of viscosity, friction, and gravity. And this energy depends on the velocity and G, which encodes the glacial geometry. And what we want to do now is to find a function that takes the geometry as input and predict the velocity that will minimize this energy. Right? So we don't know that function, so as everything that we don't know, we learn it. And we learn it in a way which is interesting because it's without any data. We can directly minimize the energy to train the network, which is very interesting because it allows us to train on the fly. So at each simulation step, we predict the velocity, and then we can backpropagate the way to correct for the mismatch in velocity by minimizing the energy. And in the same time, we do one step of glacial transport and erosion. So what is very interesting is that we can do only one step of backpropagations for each step of transport and erosion. And that's because the geometry only changes by a little between two iterations. And that allows us to build this kind of landscape that emerge from the simulation after like different glacial cycle and erosion. And we find all the features that we are looking for. So we find the U-shaped valleys, the hanging valleys, the arrays, passes, horns, circus, and lakes. So to conclude, so I work with both these tools, simulation and geometry, and so we heard a lot of talk about how to build geometry that is favorable for simulation. So I do kind of the reverse. I use simulations to build some new geometry. But for natural phenomena, there are many challenges, especially the interactions of different sub-phenomena at different scales. And the solution that I propose is to approximate the smaller scales with physical proxies, which in a way now makes a use of geometry as a proxy for helping simulation. And I gave some example with fluvial and glacial erosion. So that leaves a lot of work for the future. Can we narrow down this link between geometry and simulation? There's always this quest with unified representation. So there are a lot of talks now that wonder how we can use neural approaches to unify everything. Maybe the stochastic flow that we explored lately could be another way for this natural phenomena, because it's not only about merging simulation and geometry, but also about merging scales. Everything which happens like very far away have a very important consequences in some local features. And also there is these questions about why we should continue researching natural phenomena. I mean, there are not many in cryptographics to do that anymore. So that's very important for many applications in graphics. But I think there's also a need for synthetic, physically annotated data to train the next generation models in many situations where we don't have the means to capture the data. So we cannot really look in the past, like millions of years ago, to see how the mountains were. We cannot look in a flood, like in the extreme events, and put sensors to build data to train models. That's extremely difficult. So that's why synthetic data here is extremely important. And we see more and more that there is also cross-fertilization with specialized fields. I mean, it's not only getting information from geomorphology to build graphics applications. Now there are many graphics techniques that are used in these fields as well, right? So that's something that we can also continue to explore. So with that, I thank again very much the organizer of the conference. Thank you again for the award. Really, it's really humbling and I'm honored. I also want to thank my supervisors, my colleagues at NVIDIA, and postdoc and PhD, and also the master students and everybody who was involved in all of these works, and my friends and collaborators in computer graphics and Earth and environmental sciences. Thank you very much.
Thank you, Dr. Connie, for the wonderful paper. It's so much. I'm worked at a great time. One things library versus Parakkat, time in the mirror, create, and I just want what is the impact of full-time smart? Some eroding miles the effect the way things react to the beach. Climate and I wonder whether there is an opportunity to this reduction and whether this
So climate is an input to everything which is Earth related. So climate is an input to everything that is Earth related. So this I mean, where is it? So I mean, here, you know, this trivial equation, there is this discharge as input, but discharge depends on precipitation. Right. That's the same for glacier. So glacier, there is something which is called the equilibrium line, which is the altitude where the melting and the ablation accumulation balances, and this depends on the temperature. Right? So there is still always a bit of time in the equation, like for example here for the erosion. Yeah. And so that's where we can actually change the conditions and see how it evolves in the future. So yeah, I mean, I work with glaciologists for the ice erosion, and that's one of the main topic now, which is like especially in the ice caps at the north and south, how they will evolve in the next few years, because that's something which is actually dramatic. Mm.
based on mistakes. There's damage by chemical acts instituted the acts since September 2021. It is mostly from the RCT. Put this on for here if you could. So it's not scoring just okay. This is for people. This is super compact. Digital bridge. When from reference speech tested today, students.
Okay, thank you, Zichun. So Okay, so we know that human expressions usually lack a coherent structure, and that human expression is what I call as scribbles. And this talk is about understanding the structure from these kind of scribbles. And the core methodology is to use some kind of geometry processing. And just as a warning, this is not a formal talk about a particular work, but how my journey is or how it was. So we all know that the shapes are very important, and scientists and artists have been trying to find out a solution for how can we make imagination visible. So for millenniums or decamillenniums, people have been trying to express their imagination. You can see the old cave paintings to the recent neural networks, which can create the 3D models from just some text. And this shape modeling is very important for our community, because even if you want to do some kind of geometry processing or simulation or whatever, we need some shape to start with. And it is also crucial for many downstream applications, but you know that. However, creating these shapes are not very easy, at least for novices, because it requires some kind of artistic sensitivity, some kind of computer proficiency, and then some kind of understanding of geometry. So it's not for everyone. And for me, my ultimate goal is to make this gap between the thought process and the visual realization more fluent or more seamless. And all this without requiring any kind of expertise, technical or artistic training. And this will allow us to create fast design exploration, compounding cost savings, and physically deployable simulations. And I'm splitting this talk into 3 pieces: the works I did during my PhD, after PhD, and the recent works. So initially during my PhD time, what I was interested was in like scanning a sketch and doing some kind of processing on that. And for that, I mainly relied on delinear triangulation, which is just given set of points. We create set of triangles from them, and focused on 2 kinds of subproblems: how to complete sketches. For example, like in some kind of artistic way, people try to express their thoughts in a set of discrete set of strokes. So how can we create shapes from that? And how can we simplify artist-drawn sketches? So my first work was how to convert these sketches into shapes or discrete set of strokes into a single sketch so that we can use it for animation or coloring or whatever we want. So for that, what we did is we just took the stroke, sampled the strokes, and considered this as a curve reconstruction problem, which is like a classic problem with geometry. And we just propagate through the delinear triangulation and find the shape. However, this is only limited to shapes like which are closed, simple closed curves or open curves. So later, we extended it to sketches with cross sections or where intersections are there to create some good looking shapes. Then we wanted to somehow investigate on how to clean sketches which are drawn by artists on a pen and paper. Here, instead of considering each stroke as a single entity, we consider them as pixels. So what we did is we converted this set of pixels into a set of regions based on delinear triangulation and used that structure to simplify the sketch. Okay. And then during my post-PhD time, I was interested in more interaction. So instead of computer giving you a result, I wanted the user to be involved in the process. So this has various advantages. For example, this will allow the novice users to be part of the shape creation process because it's fun. And this will reduce the artistic effort, and it will be cost saving for us because we don't have to pay too much to artists. And finally, we will achieve superior accuracy because there is a user in the loop who will help us to update the shape that we want. So the first work what we did is something called as delinear painting. So all of you know that whenever we have a sketch with gaps, we cannot use MS Paint. So what we did is instead of considering each of this stroke as a pixel, we consider this entire region as a part that we want to color. and we encode the entire thing as a delinear triangulation. And each time when we do some coloring, we find some kind of segmentation between triangles. And this is like from this new release of Blender, this is the standard coloring tool for the Blender. And then we wanted to extend it to vector sketches because many artists prefer drawing in vector style. However, we cannot use the same algorithm for vector sketches because we need some points to start with. So what we did is we did some kind of sampling, which is called as epsilon sampling, to convert vector sketches into points. And it is guaranteed that once you do the delinear triangulation of these points, it will capture the shape. And the same criteria we use for cleaning sketches. So even if you have some roughly drawn sketch with lot of details or some kind of construction lines or overdrawn details, we can have an artist in the loop who will decide which part to keep and which part to remove. So that even from single sketch, we can create all these variations. And this is all in a way of just dragging and dropping colors, which is quite easy for anyone to understand. Okay, then we were interested in like, once we have this kind of clean sketches, how can we use it for animation? So we have some kind of sketches. So we assume that we have some kind of hidden strokes or suggestive contours. And once we have this suggestive contour, what we told is we will be able to, or we can segment the regions into small pieces. And based on the saliency, we can convert it to simple closed curve so that we can convert any sketch into some small pieces and use Adobe Illustrator or whatever to animate them. Okay, then we went away from sketches and we wanted to check whether there is anything else which is quite easy for us to create. And then we came to pixel sprites, which is quite easy. Like we know Mario game and all those kind of things, which is quite easy and simplistic to create. However, the pixel art is quite ambiguous because we have only a few pixels and all these shapes are possible from this single pixel art. So we wanted to have artists in the loop who will help us to determine the topology of the shape and the smoothness of each region. So what we did is we posed this as a like spring simulation problem where we consider the pixels as spring system and simulate them. This demo. Okay. Then recently, I am more interested in 3D shapes. Like how can we create 3D shapes and how can we manipulate them? So these 3D shapes are very interesting because we can do some rapid prototyping for various applications. And I wanted to focus on minimal representations. For example, I should be able to create shapes with simple or easy to create inputs. For instance, Lego or some drawing in VR, or I can just create some clay model and scan them, all those kind of things. And this will help diverse user bases. For instance, if there are patients with some rehabilitation or digital artists with some motor disabilities or children, it is easy for them to create these kind of shapes because they don't have to be worried about precise control of the 3D interface. And this will also help us to easily update the shape. So just before 3D shapes, I entered my 2D shapes with something called as density-based clustering. So if you have stipple kind of drawing, how can we convert this stipple drawing into some kind of density-based clustering so that we can try to understand the underlying shape? Okay, in 3D shape, like it is quite common for artists to start with an image or photograph to do their 3D modeling. However, these kind of photographs has a lot of abnormalities. For example, there will be occlusions, there will be like missing details, there will be like shadows, all those kind of things. So what we did is we came up with something called as a spine rib formulation, which will allow users to edit however they want. So user can just draw some scribble and based on that, we create this system. On that, we define a lofting surface. Then we went to reconstruction. So we know this is a long-standing problem. So what we wanted is some kind of quick feedback and without using any parameter. So what we did is we relied on, again, Voronoi balls. And based on how overlapping or how deeply intersecting Voronoi balls are, we try to group them together to create the shape we want. And this was like shown to be useful for sketches with 3D models with missing details or sharp features, noise, outliers, details, multiple topology, or even open sketches of open scans of big cities. And if everything goes well, this will be released as part of next Seagull release. Then we came to something that I'm recently interested in, how to create 3D models in VR. So from Google Tilt Brush, it is quite easy to create ribbons in virtual reality, which is like oriented strokes. And once we have those kind of strokes, can we create 3D model in real time? So that as we sketch, you can see as we sketch, we'll start getting the shape. So what we did is we employed a simple criterion, which is like filtering the Voronoi balls based on the normal direction of the ribbon. And we just blend them together to get the shape that we want. And it works for multiple genus or all those kind of things. However, it is little bit difficult to draw ribbons in 3D because we have to keep a particular wrist movement and it won't be that efficient. So we came back to drawing in sketching in 3D, which means we don't have an orientation, we just arbitrarily scratch in 3D. However, creating a 3D shape from these kind of 3D sketches is not a very easy task because the existing method use heavy optimizations. So what we wanted is again some kind of user control. So what we did is we start from these sketches, we consider them as some rigid cages, keep a balloon inside that and inflate the balloon. So as the balloon inflates, it will start capturing the shape of the sketch. But as you can see, it is some kind of iterative growing. So each step we have to grow iteratively, which won't be that interactive. Then we try to make it interactive, where we convert the sketches into a occupancy problem so that we can just employ some kind of neural network. So we use the transformer network to find the occupancy of these sketches. And once we have this occupancy, we use geometry processing to convert it to a smooth mesh. So if you are in SIGGRAPH next week, we will be presenting this paper there. And then if you attended the initial, I think first day or second day, you might have seen this thing where we have binary voxels, which is like equivalent to stacking Lego and creating smooth piecewise geometry from that. So for that, we employed some kind of deep learning along with some kind of physics-based simulation to create the shape that we want. I wait for this to complete. Yes. And finally, once we have these 3D models, we can just rely on motion lines. So those who work on comics, you know that we interpret shapes with motion lines, which is easy to represent the motion. And once we have that motion, we found or we showed that this motion can be propagated to 3D models so that user can just sketch in 2D and we'll get a 3D motion as result. Okay. So my future plan is like, can we come up with simple and predictable tools that can help people create exactly what they see in their mind? So all of us know there are like a lot of deep learning techniques to do that thing, which is quite simple. But my objective is not at all to use deep learning. And my objective is to have the process more creative and enjoyable. So it is not just the result. I want that process to be enjoyable. And I want to ensure that even if you don't have any technical skills or artistic training, you should still be able to create the shape that you have in your mind. And in long term, I would like to preserve the sanctity of the creative process so that instead of just giving a prompt and getting the 3D model, I will get the feel of creating something by myself and empowering the latent artist. So I believe all of us are artists. We have something inside us. So even if you don't show to others, we just sketch by ourselves just for fun. So I want that artist to be grown and radical accessibility. So eventually, like we know that we have speech, but depending on which part of the earth you are from, you might not be able to communicate with others. But instead of that, we can just sketch and everyone will be able to understand. So my focus is to go towards that universal language of sketching. And finally, towards the motto of anyone can model and everyone should model. And all of this work wouldn't have been possible without my advisors, my co-authors sorted in their first author name, and many of my students. And thank you. Yes. Thank you. Yes, we would like to we are trying to use some kind of deep learning so that even if you scribble in CAD model, you should be able to create something like editable and easy to creatable. So we are working on that, and hopefully we'll do something soon. Mhm. In which one? So in our system, it is like everything is organic. So we don't have to care about we assume that everything is smooth and it is quite easy. But in CAD, it's not very easy because if you sketch something, we don't even know what is sharp or which one we want to be sharp. Yeah, thank you. Thank you.